Welcome to section 11.3. Now, a little preamble here is that we have learned that if we have a geometric series, we know the exact value of the answer, provided that R is the right size. Now, also, telescoping series work just as well. They cancel and we can get exact values. Now, the reason that we don't focus on exact values more than that is because this is about the best that we can do until we develop more techniques. So what we focus on is to look at series and ask, converge or diverge? Why? If it's convergent, we might add them up. If it's divergent, well, probably not useful. So what we're going to do is we're now going to make use of something very powerful, the relationship that integrals have to series. And it turns out that Riemann sums are very, very nice. I'm going to look at one well-known series. Now, if you think of this series as nothing more than evaluating the function at n, the function f of x equals 1 over x squared. Now, this function has a asymptote at 0 and comes down like this. And I'm going to point out there's a very nice picture that relates this series to the integral. First off, I'm going to plug in 1 and get 1 over 1, 1. And then I'm going to plug in 2 and get 1/4. And I'm going to plug in 3 and get 1/9. And I'm going to observe that the lower Riemann sum on the integral would look like this. Now, what's really neat about this is that in some sense, if I just do the integral from 1 to infinity, then all of the things except for the first term are less than that. I'd like you to notice that this is fairly reasonable, that the integral from 1 to infinity of 1 over x squared dx would be this area, which would be greater than, because you can clearly see that, the series starting at 2 of 1 over n squared. And so if we add this box to it, well, that's just the whole series. And we would have an upper bound to what the value of 1 over n squared is. So the question is, can we do that integral? Sure, let's do this. Off to the left here, we're going to do the integral from 1 to infinity of 1 over x squared dx, which is minus 2 over x cubed, evaluated from 1 to infinity, which is 0 minus 2, which is 2. So 2 plus 1 is greater than the value of our series. Now, what's neat about this is we had a theorem before that said if a series is bounded above, then it's convergent. So this thing must converge. But I don't know to what. So, well, that's a very useful little fact there. So now let me look at an upper Riemann series. So suppose I had taken that function and instead I had done this and did upper Riemann sums. Well, then I could get a bound that my series from some point, some starting point, whichever this one is, will be bigger than an integral from that same starting point of a function. So that's kind of neat, because when we use the lower one, this is bigger equal to some part of the series, might be a different starting point. So, and this is really powerful. We're going to use integrals to start understanding the size of these values for these series. All right, so let's do an example of an upper Riemann sum. So let's ask ourselves about what do we suppose that the sum of 1 over the square root of n equals 1 to infinity would look like. It's 1 over root 1, which is 1, plus 1 over root 2, plus 1 over root 3, plus 1 over root 4 is 1/3, sorry, 1/2, plus. Now, by the way, for those of you that are really sharp, I want you to notice that we talked about the harmonic series before. And here, and later on, 1 over the square root of 9 will be 1/3 there. This series has within it the harmonic series, which we mentioned diverges. This diverges. But how can we see that without that certain amount of trickery? Well, what we're going to do is we're going to draw the function f of x equals 1 over the square root of x, which looks much like the other function we had there. And we're going to plug in values into it. 1 over root 1 is 1. But then I'm going to use and calculate the upper Riemann sum on that. And now we're going to put in 2, 1 over root 2, that's this height, 1 over root 2. But then I'm going to look at the upper box. And then I'm going to put in 3, 1 over root 3. This is 1 over root 3. And then go this way. Now, what this shows is that our series, the sum, starting at 1 times the width 1 is the a sub n, that box. So this is 1 over root n, starting at 1 and going forever, are those green boxes. Width 1, height f of x, that's what they add up to. But these green boxes are the upper Riemann sum. They're bigger than the integral from 1 to infinity of 1 over root x dx. But the integral of 1 over root dx is, well, it's a minus 1, add 1 to the power, we get root x, and we have a 2 in front, and then it's from 1 to infinity, and the answer is twice the square root of infinity minus 2. That's divergent. This is a huge number. This is bigger than a huge number. Interesting. The integral allows us to look at functions, series rather, and guess at their values. So we know it's bigger than certain Riemann sums, less than other certain Riemann sums. So now, it turns out there's something called the integral test. And we are going to develop several tests to determine if a series diverges or converges. So here we go. The integral test. Now, it's going to be used on a positive series, so that's what we want to look like. So we're going to make sure that f of x is defined on 1 to infinity, and the series a sub n is a positive series. And let's also have the a sub n be start at 1 and go to infinity. Okay. Now, if a sub n is really f of n evaluated, then we have a very interesting theorem. The theorem says, part A, if the integral of f of x from 1 to infinity converges, then the series converges. And if the integral from 1 to infinity of f of x diverges, then the series diverges. So the series does what the integral does. Now, there's no bounding upper and lower here. It's just simply saying if we do the convergent series, then we get a convergent, if we get a convergent integral, we get a convergent series. And if we do a divergent integral, we get a divergent series. And so that means that it's very simple for us to ask ourselves what some series behave like. So let's do the following. Let's do this series. The series from n equals 1 to infinity of 1 over n cubed. Well, 1 over n cubed is really f sub n, where f of x equals 1 over x cubed. The integral of 1 over x cubed dx from 1 to infinity, that's minus 3, so it's minus 1 half x to the minus 2 from 1 to infinity, which is 1 over 2 infinity minus 1 half. That goes to 0, why the answer is 1 half. That's convergent. Therefore, we conclude this thing converges. Maybe we should add it up and see what it equals. It's that simple. Now, it turns out there are many integrals that we know how to do. So anytime a function is associated with an integral we know how to do to infinity, and it's associated with a series, then we have an idea if the series is going to converge or diverge. A whole class of functions. So let's start with this one. Let's define a sub n to be equal to f sub n, where f of x is 1 over x, and we put a p there for traditional reasons. This means a sub n is 1 over n to the p. So the series 1 over n to the p n equals 1 to infinity, is associated with the integral from 1 to infinity of 1 over x to the p dx. But this integral we know how to do. You add 1 to the power, so it's x to the minus p plus 1, so it'll be x to the 1 minus p over 1 minus p evaluated from 1 to infinity. And so this is going to be basically infinity, the 1 minus p over 1 minus p minus, minus 1 over 1 minus p. So, if that p is bigger than 1, that infinity is in the bottom. That's what happened on this page. Since that p was bigger than 1, that x squared ended up in the bottom, so that goes to 0. Very powerful. So what happens if p is bigger than 1, then this term is 0, and you get the answer 1 over p minus 1. To make it positive, you get convergence. So if p is bigger than 1, this converges. Now, if p is less than 1, like we saw 1 over the square root of x, when we did this one with 1 over the square root of x, we found the integral to be infinity. So if p is less than 1, then that thing is divergent. This is called the p-test. So again, it tells us when we're working with specific series whether or not they converge. Well, that's extremely useful that we now know when series converge or diverge, but we don't really know what they add up to. So now we're actually going to do a numeric application of the integral test. But it's not actually of the test, of the integral method. Now, in order to do this, I'm going to very, very clearly draw two pictures. And we're going to draw the picture at a point in the sequence where we're at n and we're in n plus 1. So I'm going to plug in n into my function. Here's my f of x. So this height right here is going to be f of n, which is a sub n. And when we move over to n plus 1, that's with 1, this box, as we've seen before, is the area A sub n. And this box is the area A sub n plus 1. And we do that forever, which says that if you add up starting, now you have to have, since I put n here, I have to have a different index. I starts at n and goes to infinity of a sub I, so an plus 1, etc. This is bigger or equal to, if we have a very strange function, the integral from n to infinity of f of x. A fact. Now, I am going to do a lower Riemann sum. So, I am going to start at n minus 1, go up here over, here's n, up, over, so this, oh, made a mistake. Okay, so now we're going to do a numeric application. And it is associated with integrals. Now, integrals. We're not actually going to do the integral test, but we're going to use the Riemann sum process. So first I'm going to draw my function f of x, which has the property that it produces the rule for a sub n. And I'm going to put the number n here, n plus 1. And n plus 1 I'm going to go up, but I'm going to draw my box to the left. And so 1 times f of n plus 1, well, this will be area an plus 1. Then I'll go over n plus 2 and go up, and then back over 1. This will have area an plus 2. And we'll do this forever, which says that if we start at an index of n plus 1 of ai and go forever, all of these boxes are less than, and for some strange function maybe equal, to the integral, but the integral starts at n and goes to infinity of f of x dx. So this area is bigger than my boxes that. Now we're going to draw a similar picture, but this time I'm going to use upper Riemann sum boxes, and I want the first box to have height n plus 1. So I've got to put in n plus 1 here to get height a of n plus 1, and so this area is an plus 1. So now I'm at n plus 2. That height over 1 is of area an plus 2. So these boxes and those boxes are the same. They're just starting at different places. So what's this picture say? It says that if we add up my index starting at n plus 1, and I go to infinity, and we put ai here, those boxes are greater than or equal to, well, not the same integral. It's the integral from n plus 1 to infinity of f of x. Huh, what can I do with these two facts? Well, first off, let's make a definition. Suppose we just want to add up the first n pieces of our series. It approximates our series. Then what's left is those boxes here from n plus 1 to infinity, which I've drawn two inequalities. So this is often referred to as the R sub n of a series. Why R sub n? Because you've done n terms in this series, and this is the remainder of what has to be calculated after n additions. This is what our series adds up to. All right? Now, if you take and rearrange the inequalities that I just had there, then it's this that we understand. We understand the following, that remainder, that thing called r of n, is less than or equal to the integral from n to infinity of our f of x dx. But it was greater than or equal to our integral from n plus 1 to infinity of our f of x dx. Here it was. Our remainder was bigger than the n plus 1, but our remainder was smaller than that integral. So this says something very interesting. It says we understand to a certain degree what's left. We can calculate this. So you know what I'm going to do? I am going to now multiply this by a minus 1. Then I'm going to add s everywhere.